Hello, I'm Dr. Brent Harrison, assistant professor here at the University of Kentucky. Today, with my colleagues Dr. Stephen Ware, Chungshi Lee, and Anton Vinogradov, we'll be presenting our work on hierarchical abstract process modeling for analyst workflow.
The goal of our project is to build a visualization that summarizes how a group of intelligence analysts approach a task. We're building this visualization from the bottom up, based on data logged from actual analysts. The data comes from a serious game that simulates the kind of work that analysts do. In this game, you're investigating a cybercrime in a small startup company. The police suspect an insider attack, meaning one of the employees stole sensitive software from the company. Your job is to dig through a database of many different kinds of documents, including emails, websites, network logs, and calendar entries to uncover the culprit. The game provides tools that allow analysts to search the database of documents using many criteria. Analysts can read the documents they find and visualize groups of documents on a map and a timeline. There's also a simulated web search engine that allows them to learn more about the fictional company and characters, and a tool to recover deleted files from an employee's computer. When an analyst finds a useful search query or a useful document, they can save it for later. Saved queries and saved documents can be assigned as evidence for or against each employee of the company. With a lot of help from the Laboratory for Analytic Sciences at North Carolina State University, we logged over 6,000 events from 20 trained analysts. Last year, we used a narrative structure learning technique to build graphs which visualize the events analysts commonly did on their way to reaching their final conclusions. But there were several ways that this visualization needed to be improved. First, showing individual events, like reading a specific document, was too fine-grained, because either the graph was too large to read or it left out too much information. We want to group events together into meaningful units. Also, the structure learning technique that we used doesn't allow for loops, and we found that analysts frequently doubled back, revisiting old search queries or rereading documents. We want our visualization to be able to express this cyclic process. Here's our improved process. First, we grouped related events in each user's log into segments. Then we compared those segments across users to find common activities and grouped those common segments together into clusters. Then we built a graph out of those clusters and applied some simple pruning techniques to make the graphs more readable. Let's suppose we have the following events from two different users. The first step is to group sequential, related events into meaningful segments. We explored a few different ways to do this. In this example, we assumed that a search event always begins a new segment. After segmentation, we want to figure out when two users are effectively doing the same thing. This is challenging because when two people are reading Michelle's emails about cargo, they might not do exactly the same events in exactly the same order. We explored several solutions for recognizing when two segments were the same, including neural language models, neural event encoders, lexicographic comparisons, agglomerative clustering, and density-based clustering. We built a graph out of our final clusters, which represent high-level tasks that a group of analysts carried out, and the order in which they occurred. Sometimes these graphs were still too large to be easily read, so we also explored a few simple pruning techniques, such as removing tasks which only a small number of analysts did.
This interactive tool shows the clusters, how they are connected, and the events that make up each cluster. The tool allows us to view the graphs and manipulate the nodes. The nodes and the edges have extra information that can be viewed by mousing over, generally showing which users are associated with that edge and the weight of the edges. The nodes are color-coded such that the darker colored nodes have more users. Basic manipulation, like selecting specific nodes, moving the nodes around, and deleting nodes, is available to better explore the data. To showcase the tool, we can look at an example clustering method. The clustering method shown here is search, read, save clustering, pruning nodes with less than 5 users and edges that have less than 2 users. Here we select the cluster that represents when users found incriminating evidence. Leading up to this, most users were investigating Daryl or the trade show. By double-clicking on a node, we can see which event it consists of. Events that are deemed similar enough are combined, as can be seen on this Read Email 06, Looking for a Job node, which is where the users read the incriminating evidence. We can see that while users used a variety of searches to find this document, afterwards most users either immediately went on to save it or went to read the reply. Nodes that include justification, like saves and searches, show a user's justification when moused over. Afterwards, some users went on to find more evidence, while others did not. Since this is a pruned graph, clusters that were done by too few users are not shown. Other methods can be loaded into this tool to visualize the data from multiple clustering methods, like density-based clustering for search-read-save segmenting, or save clustering for save segmenting.
Recall that the goal of this graph was for it to serve as a generalization of the analytic process. To test this, we decided to train a neural network that could predict what's the next cluster that a user is likely to visit, based on their past clusters visited. Using this network, we could better tailor interventions for a specific user based on what they're likely to do at some point in the future.
Our initial evaluation was to see if our machine learning model could predict the next cluster a user would visit based on their history. To measure this, predict the overall accuracy of our model in predicting the next cluster that a user would visit compared against a random baseline model. The random baseline model would simply predict a random cluster for each example. Our results show that our model significantly outperformed the random baseline model. However, both models perform overall very poorly, as our model achieved an overall accuracy about 30%. This caused us to further investigate the quality of our model by performing a new evaluation task. We extended our evaluation by investigating whether the cluster predicted by our model would appear at any future point in a user's trace. In other words, where a user eventually visits the cluster that our model predicts, we refer to this as future cluster accuracy. In this evaluation, we compare against two baselines, the random baseline and a baseline that always predicts the last cluster that a user visits. Notably, this baseline will always achieve 100% accuracy on this task. As we can see, our model performs very well at predicting future clusters compared to the random baseline. The last cluster baseline, however, points out a potential issue with this evaluation. One can simply predict common clusters that occur at the end of traces and still achieve high accuracy. This leads to our final set of evaluations. In our final evaluation, we discount accuracy based on its distance from the next clusters a user would perform. In this way, predicting clusters that a user is likely to visit in the near future would result in higher scores than always predicting the final cluster a user would visit. In this experiment, we discount future events based on a discount factor of 0.8. We compare against the random baseline and the last cluster baseline for these experiments. As you can see, with this additional discounting, our model now outperforms both of our baselines. We feel that this provides strong evidence that our model can accurately predict future actions that a user is likely to perform in the near future.
Thanks for listening. This work was a shared effort between the CORGI lab and the Narrative Intelligence lab at the University of Kentucky. We would also like to thank the Laboratory for Analytic Sciences for their support, especially the content triage team.